This module looks at confidence intervals. We'll discuss their interpretation and how to construct confidence intervals in some standard situations. It's important to have a solid grasp on these concepts because most statistical analyses provide some kind of confidence interval. Let's look again at the US presidential approval ratings. There are about 140 million likely voters. And let's suppose for a minute that 60% of them approve of the way the president is handling his job. Now we do a poll. Let's say we poll 1,000 of them. The approval percentage we get in the poll should be somewhat similar to 60%, but it will be off a little bit. How much will it be off? Well, we already know that the sample percentage is likely off by about 1 standard error. Oftentimes, one would like to have a statement that is somewhat more precise. This is done by a confidence interval. We already know that according to the central limit theorem, the sample percentage follows the normal curve with expected value equal to mu equal the population percentage and standard error equal to the population standard deviation sigma divided by square root sample size. In this case, sigma turns out to be 0.49. To compute that, recall that we are looking at the case where we are counting things. Namely, we are counting voters who approve of the president. So we introduce labels where each voter who approves gets a 1 and every other voter gets a 0. And there are 140 million voters, so we end up with 140 million labels. And from that, we can compute the standard deviation sigma as 0.48. So what this means is that there is a population percentage mu, which is 60%. And then if we sample 1,000 voters, the sample percentage will follow the normal curve. And the empirical rule says if we go 2 standard errors each way, then there's a 95% chance that the sample percentage will be somewhere in that range. So we know that there's a 95% chance that the sample percentage is no more than 2 standard errors away from the population percentage mu. But saying that the sample percentage is no more than 2 standard errors away from the population percentage mu is the same as saying that the population percentage mu is no more than 2 standard errors away from the sample percentage. What this means is we can take our sample percentage, for example, it may turn out to be 58%, and then we go 2 standard errors in each direction, and that gives us a range of plausible values for the population percentage. Remember, when we do a poll, we do not know the population percentage. The whole idea is to take a sample and get the sample percentage, and hopefully the population percentage will be close to the sample percentage. So what we do is we take the sample percentage of 58%, go 2 standard errors in each direction, which takes us to 54.8% and 61.2%. And the interval between these two numbers is called a 95% confidence interval for the unknown population percentage. So why is this called a confidence interval? Where does the name confidence come from, and why don't we simply say probability? Well, the population percentage mu is a fixed number, and that number is either inside the interval or outside the interval. So once we write down the confidence interval, there are no more chances involved. And for that reason, we talk about confidence. The randomness in this procedure comes really through the sampling. If we sampled another 1,000 voters, we will get a slightly different interval. So the interpretation of a 95% confidence interval is that if we do many polls, and for each poll we do a confidence interval, then 95% of these intervals trap the population percentage, and therefore 5% will miss it. The number 95% is called the confidence level that comes with a confidence interval. Here is a picture that explains the situation. There's some population percentage mu, let's say it's 60%. And then we take a sample of size 1,000 and we compute a confidence interval. For example, that confidence interval might be from 55% down here to 65% up here. And you see in this case, the confidence interval traps the population percentage mu. Then next week, Gallup might do another poll, and it comes up with another confidence interval. And that might run from here to there. And somebody else might do a third confidence interval, and it may be from here to here. And another poll may result in a confidence interval from here to here, and now you see this one misses the population percentage. So among this large number of 95% confidence intervals, most cover the population percentage, but some don't, like this one will not, and this one will not. The way a confidence interval is reported is oftentimes something like, I'm 95% confident that the president's approval rating is between 54.8% and 61.2%. And the interpretation of this is that 95% of the time I'm correct when making such a statement, and 5% of the time I may be wrong. So keep in mind that the randomness is in the sampling and not in the population percentage. The idea of a confidence interval is that it gives a range of plausible values for a population parameter which we call mu. Usually a confidence interval is constructed around an estimate for mu, which oftentimes is some form of an average. Let's look at some examples. In the first example, the population parameter mu we are interested in is the approval percentage among all 140 million likely voters. As an estimate, we use the approval percentage among the voters in our sample. This percentage is an average in our usual counting schemes where we have 0 and 1 labels. As another example, suppose we want to measure the speed of light. In that case, our estimate would be the average of, say, 30 measurements. A key point now is that if we use averages, then we know that the central limit theorem applies. Therefore, we have a very simple form for the confidence interval, which is simply the estimate plus minus a z-value times the standard error. And that z-value simply comes from the normal approximation. Which z-value should we take? Well, that depends on the desired confidence level. For example, if we would like to have a 95% confidence level, then we get z equal 1.96. That comes from normal approximation, where we look at the value of z such that 95% lies in the middle. That value of z is 1.96, or oftentimes we simply use 2. On the other hand, if we were interested in a 90% confidence level, then we would find z equals 1.65. And for a 99% confidence level, we would get z equal 2.58. The third number which we have to write down for our confidence interval is the SE. That's the standard error of the estimate. If the estimate is an average, for example a percentage, then we know that by the square root law, the standard error is sigma over square root sample size, where sigma is the standard deviation of the population. So now we have a small problem because we need to know sigma, but we don't, because sigma is the standard deviation of the population and we don't know what the population is. A way out of this is to simply estimate sigma from the sample. That is, we use the sample standard deviation in place of the population standard deviation. That's a very simple idea, and we will see later that this idea can be used in much more complicated situations. For that reason, it has a name. It's called the bootstrap principle. Let's look at the earlier example. Suppose we poll 1,000 likely voters and find that 58% approve of the way the president handles his job. So the formula for the standard error of the percentage is sigma over square root n, and then we can convert into a percentage simply by multiplying with 100%. And sigma is given by square root p times 1 minus p, where p is the proportion of all voters who approve. That's simply using a formula which we looked at earlier. So in this case, p is unknown to us. because we don't know the proportion of all 140 million voters who approve. The bootstrap principle then says to replace sigma by S, which is the standard deviation of the 0-1 labels in our sample. And if we compute that standard deviation, we get square root 0.58 times 1 minus 0.58, which is 0.49. And by the way, that's exactly the same answer we would have gotten if we had plugged in, instead of p here, our estimate from the sample. So now we can write down our 95% confidence interval for p. The formula says we take the estimate in our sample, which is 58%, then we do plus minus z, and since we have a 95% confidence level, we take z equal to 2. And then we have the standard error, which has the formula given above, so we get 0.49 divided by square root sample size, and we can write this as an interval 54.9% to 61.1%. Now let's look at our second example, where we estimate the speed of light using the average of 30 measurements. So now in this case, what's the population or the probability histogram we are sampling from? We have to think through that question first before we can apply the bootstrap principle. Now, the reason why we get 30 different measurements in the first place is because each measurement is off by a chance error. So we have a model where each measurement equals the true speed of light plus a measurement error. And we can think of the measurement error as a random error. This chance error follows some kind of probability histogram that we don't know. But we can use the bootstrap principle to estimate the standard deviation of this probability histogram using the standard deviation of the sample. By the way, the reason why this works is that we are looking at the standard deviation S of the measurements on the left-hand side, and we want to use that standard deviation as an estimate of the standard deviation sigma of the measurement errors on the right-hand side. So notice there is an added term, which is the speed of light, but remember that adding a fixed number to the measurements will not change the standard deviation. That's the reason why the bootstrap principle works in this case. Later on, we will see how we can use the bootstrap principle in even more complicated situations than these. Now let's have a look how big the confidence interval is. Remember, the formula for the interval is we take the estimate plus minus z times standard error. So the width of the confidence interval is given by twice z times standard error. That term z times standard error is called the margin of error. So remember, the square root law says that the standard error is given by sigma over square root n. And what that means is that the width goes down as the sample size n increases. However, because there's a square root there, that means that if we want to cut the width in half, we need 4 times the sample size. And likewise, if we wanted 1/10 of the width, we would need 100 times the sample size. Another option to make the confidence interval smaller is to make z smaller. Remember, z is determined by the confidence level. So we can make z smaller by choosing a smaller confidence level. For example, instead of using a confidence level of 95%, we could use 80%. So there's a trade-off here. We would get a smaller confidence interval at the cost of having less confidence that it covers the true parameter mu. If we are interested in confidence intervals for percentages, then there's a simple rule of thumb that allows to compute these confidence intervals on the fly. The rule of thumb says just take the estimated percentage plus minus 1 over square root sample size. The reason why this works is because sigma can be shown to be never larger than 1/2, no matter what the population parameter p is. So if we plug this into our formula for the standard error, we see that z times standard error, well, z equals 2, and sigma is not more than 1/2, and those 2's cancel out, and so we are left over with that rule of thumb. Sometimes newspaper articles give confidence intervals without stating a confidence level. In that case, it's tacitly assumed that the confidence level is 95%. Tests of significance are another mainstay of statistical analysis. We will look at the logic behind testing and then discuss some important tests for situations where one wants to assess one sample or compare two samples. We also discuss some common misunderstandings and pitfalls in testing. Suppose we toss a coin 10 times and we get 7 tails. Now we can start wondering whether the coin is fair. So the question becomes, is getting 7 tails sufficient evidence to conclude that the coin is biased? This is a question that's being addressed by what's called hypothesis tests. First, let's look at some terminology. The null hypothesis, which is sometimes written as H sub 0, says that nothing extraordinary is going on. So that's a very generic description, and we will look at some cases to see what that means. In the case of coin tossing, nothing extraordinary simply means that the coin is fair. So in other words, we can write the null hypothesis as saying that the probability of getting tails is a half. Then there's a second hypothesis called the alternative hypothesis. It says that there's a different chance process at work. So in our example, the alternative hypothesis would be that the probability of getting tails is not equal to 1/2. The idea of hypothesis testing is to collect data and then to check whether the data are compatible with the null hypothesis or not. If we find that the data are not compatible with the null hypothesis, then we reject the null hypothesis. Let's look at a different example. Suppose a company develops a new drug to lower blood pressure. Then it tests the drug with an experiment that involves 1,000 patients. Remember, the null hypothesis always means nothing extraordinary is going on. In this case, nothing extraordinary means that the drug has no special effect. So our null hypothesis in this case becomes that there is no change in the blood pressure of the patients, whereas the alternative hypothesis is that there is a blood pressure drop. So if you put yourselves in the shoes of the company, you see that in this case, your goal actually is to reject the null hypothesis. So oftentimes the logic behind testing is indirect. One assumes that nothing extraordinary is happening and then hopes to reject this assumption. So now let's look how we would go about actually doing a test. The first step is to come up with a test statistic. A test statistic measures how far away the data are from what we would expect if the null hypothesis were true. A common test statistic is the so-called z-statistic. The z-statistic looks at the observed outcome minus the expected outcome divided by the standard error. Here, the observed outcome is a statistic that is appropriate for assessing the null hypothesis. For example, when we toss 10 coins, an appropriate statistic would be the number of tails, or maybe the percent of tails. Expected here stands for the expected value of the statistic, assuming that the null hypothesis is true. Likewise, the standard error is the standard error of the statistic under the assumption that the null hypothesis is true. Let's look at our above example. Our statistic was the number of tails. And so using the formulas for the expected values of sums, we find that the expected value is 10 times the probability of getting a tail, which is 5. And using the formula for the standard error, we get the standard error for the sum is 1.58. So our z-statistic becomes the observed sum, that is the number of tails, which is 7, minus the expected, which is 5, divided by the standard error, and that gives us a z-value of 1.27. The idea of a test statistic, such as the z-statistic, is that large values of the absolute value of z are evidence against the null hypothesis. Why is that? So remember, z is the observed minus expected over the standard error. So if the absolute value of z is large, that means there's a big discrepancy between observed and expected. So the larger absolute value of z is, the stronger the evidence. So the last piece of hypothesis testing that's missing is we have to find a way that converts the size of z into some measure of evidence. And that measure is given by the p-value, or sometimes it's called the observed significance level. The p-value is the probability of getting a value of the z statistic that is as extreme or more extreme than the observed one, under the assumption that the null hypothesis is true. So that sentence might be a bit difficult to digest, and it's best to look at some examples. To see what's going on, we already know that under the null hypothesis, the z statistic follows the standard normal curve by the central limit theorem. That is simply because we have an observed sum minus expected sum over the standard error. So this is simply standardizing a sum, and we know by the central limit theorem that follows a normal curve. What that means is that the p-value can be computed using normal approximation. Let's look at this picture here. We have a standard normal curve, and then suppose we have an observed z-value here. And now the p-value is the probability of getting z as extreme or more extreme than the observed one, so that would be here, or to the left of negative z. So the p-value is this shaded area there. And now you get the idea that as z gets large, that shaded area gets small. So a small shaded area is evidence against the null hypothesis. Oftentimes, the criterion for rejecting the null hypothesis is having a p-value that is smaller than 5%. Then the technical term for this is that the result is statistically significant. Let's look at our example about coin tossing. We have an observed z statistic of 1.27. So that's somewhere here. Turns out the area to the right of 1.27 is 10.2%. So the p-value is the probability of getting a normal outcome that's larger than 1.27 or smaller than negative 1.27. And since the normal curve is symmetric, we simply double the shaded area. So we find that the p-value in this case is twice 10.2%, so it's 20.4%. So what would be the conclusion in this case? Well, 20.4% is not smaller than 5%, so we would not reject the null hypothesis. And so remember the interpretation of the p-value. If the coin is fair, then there's a 20.4% chance to get such an extreme outcome. So in other words, that's actually not very surprising, and that means there's not enough evidence to reject the null hypothesis. But keep in mind that the p-value does not give the probability that the null hypothesis is true. That's because the null hypothesis is either true or not, and there are no chances involved in that one. Rather, what the p-value does is it gives the probability of seeing a statistic which is as extreme or even more extreme than the one you observe, under the assumption that the null hypothesis is true. So let's apply testing to a taste experiment. It's actually surprisingly difficult to distinguish Coke and Pepsi by taste alone. That means you're not allowed to see what's on the can. I did an experiment about this in a class at Stanford where 10 cups were filled at random with either Coke or Pepsi. Then a student volunteer tasted each of the 10 cups and correctly named the contents of 7. So the question is whether this is sufficient evidence to conclude that the student can tell apart Coke and Pepsi. So what's the null hypothesis in this situation? Remember, the generic expression for null hypothesis is nothing extraordinary is going on. In this case, that would mean that the student does not have any special ability to tell Coke and Pepsi apart. In other words, the student would just be guessing. Now we have to write this down in a way where we can introduce our methodology. So we know that when we count things, we will introduce 0-1 labels. So in this case, we may have 1 for a correct answer and 0 for a wrong answer. Then the null hypothesis would simply say that the probability of a correct answer is a half, and the alternative would be that the probability of a correct answer is larger than a half. This is called a one-sided test, and that simply means that the alternative hypothesis is on one side of the null and not on both sides. So in this case, the z-statistic looks exactly like the one we had for coin tossing. We have observed sum, which is 7. The expected sum in 10 trials would be 5. And then we have the standard error of the sum in the denominator, and we found that to be 1.58. So the z-statistic comes down to 1.27. So next we have to find the p-value. So we have a standard normal curve, and we look at a z-value of 1.27, and the area to the right turns out to be 10.2%. And remember, we do a one-sided test, so we're not going to double that one. And finally, the conclusion is, since 10.2% is not smaller than 5%, we don't reject the null hypothesis. So there's not enough evidence to convince us that the student can distinguish Coke and Pepsi. For this experiment, it might actually be also appropriate to do a two-sided test. That is, we would look at the alternative that the probability of a correct answer is different from a half. This alternative would correspond to a student who can distinguish Coke and Pepsi, but who may confuse which is which. For example, such a student might get one correct answer. So very few correct answers are actually evidence that the student can distinguish Coke and Pepsi, but he would mix up the two. And that actually happened once when I did the experiment. In general, you have to think carefully ahead of time whether the alternative should be one-sided or two-sided. Keep in mind that for a two-sided test, the p-value gets doubled. If one does a two-sided test and it's not significant, then it may be tempting to declare that one wanted to do a one-sided test in the first place and cut the p-value in half to get it under the 5% threshold. That is not okay. So you have to declare ahead of time whether you want to do a one-sided test or a two-sided test. When the sample size is small, then we need to apply a small modification to the z-test. Let's look at this example. The health guideline for lead in drinking water is a concentration of not more than 15 parts per billion. Now suppose we have 5 independent samples from a reservoir and they average to 15.6 parts per billion. So that's above the threshold of 15 parts per billion, but it could be due to measurement error. So the question is this sufficient evidence to conclude that the concentration mu in the reservoir is above the standard of 15 parts per billion? So the first thing here is to think how our measurements come about. Remember the model we had for measurements. A measurement is the true value mu plus some chance error. And that chance error explains why it's possible to get an average of 15.6 even though the true concentration in the reservoir mu might actually be 15 or below. So our null hypothesis would be that the true concentration mu is 15 parts per billion, and the alternative would be that it is larger than 15. So by the way, why are we looking at a null where the mu is exactly 15? The reason is that this is kind of a worst-case scenario. The p-value we get in that case is larger than the p-value we would get for smaller null hypotheses. And so if we can reject in this case, we can also reject in others. So let's try a z-test for this case. The z-statistic looks at the observed, and in this case, we are looking at averages. So we have observed average minus expected average over the standard error of the average. So we know the observed average is 15.6. We know the expected average, that's simply the value under the null hypothesis, is 15. And the only thing we need to figure out is what's the standard error of the average. We do have a formula for the standard error of the average. It's simply the standard deviation sigma divided by square root sample size. But now the problem is that we do not know the standard deviation sigma of the measurement error. As usual, we would simply estimate sigma by S, which is the sample standard deviation of the measurements. Here's where the complication comes in. For small sample sizes, let's say smaller than 20, if we have to estimate sigma, then the normal curve is not a good enough approximation to the distribution of the z-statistic. What happens is that the uncertainty in estimating sigma throws off the approximation. In that case, we have to use a slightly different approximation, which is called students' t-distribution with n-1 degrees of freedom. Here's a graph that shows several student curves. The black curve with nu equals infinity actually corresponds to the standard normal curve. So what you can see is that the t-curves are somewhat lower in the middle, but the tails of the t-curves are higher up. These fatter tails simply reflect the additional uncertainty that comes in from estimating sigma. If the sample size is large enough, then this additional uncertainty is not relevant, and therefore we can simply use the standard normal curve. By the way, there's an interesting story as to why this whole thing is called students' distribution. It was actually derived by a beer brewer with the name Gossett, and he was working for the British Guinness Brewery. But the brewery did not allow its employees to make their work public, so he published these results under the pseudonym Student. When using the t-test, keep in mind that your estimate S for the sample standard deviation has n-1 in the denominator, not n. That's really important for the t-test. The way you should think about the t-test is as a special case of the z-test that becomes necessary when the sample size is small. In that case, it's also better to replace the usual normal confidence intervals by a t-interval. That is, instead of using a cutoff z, we would use the appropriate cutoff t with n-1 degrees of freedom. The name degrees of freedom is simply a technical term. That means for every sample size n, there is a student curve. And the one we're going to use is the one with n-1 degrees of freedom. Here are some more facts on testing. The first one is particularly important. It says that statistical significance is not the same thing as practical importance. What does that mean? Suppose in our example, the sample average of lead concentrations is just slightly above the health standard of 15 parts per billion. For example, the sample average could be 15.05 parts per billion. Now, that may not be very relevant. After all, it's essentially the same thing as 15. But it may turn out that the statistical test we just did is highly significant. How can that be? Well, statistical significance simply says that we can be confident that the effect is there. It doesn't say how big the effect is. So how can it be that a small difference, such as going to 15.05, will result in a highly significant test? Well, the answer is the square root law. A large sample size makes the standard error small because the sample size is in the denominator. And with a small standard error, we may quickly get a very significant test result. For that reason, it's helpful to complement a test with a confidence interval. In that case, we might get a confidence interval that, for example, goes from 15.02 all the way to 15.08. And that, in effect, tells us that we can be confident that we are not far away from the health limit. It turns out that there's a general connection between confidence intervals and tests. A 95% confidence interval contains all values for the null hypothesis that will not be rejected by a two-sided test at the 5% significance level. Now, that's a difficult statement to digest. The best way to think about this is in terms of the previous example. Rejecting the null hypothesis of 15 is the same as saying 15 is not in the confidence interval. Finally, keep in mind that there are two ways that a test can result in a wrong decision. It may be that the null hypothesis is true, but we erroneously reject it. This is called a type 1 error, or you may know it under the name false positive. The second type of error, which is called type 2 error, occurs if the null hypothesis is not true, but we fail to reject it. Remember, the standard rule for rejecting a null hypothesis is when the p-value falls below 5%. If that's the rule, that means that the probability of a type 1 error is at most 5%. Now let's look at a slightly different situation where it turns out we can use a z-test. Last month, the president's approval rating in a sample of 1,000 likely voters was 55%. This month, a poll of 1,500 likely voters resulted in a rating of 58%. So the question is whether that's sufficient evidence to conclude that the rating has changed. In this case, we want to compare these two percentages. The first step is to find a way to write this down as a null hypothesis. So what we do is we write P1 for the proportion of all likely voters which approved last month, and P2 for the proportion of voters approving this month. So remember, the null hypothesis means that nothing unusual is going on. So that means P1 equals P2. It's easier to look at the difference of these two numbers, and then the null hypothesis becomes that the difference is 0, and the alternative is that the difference is not equal to 0. Of course, each proportion is estimated by its corresponding percentage. So now the key point is that the central limit theorem applies to the difference just as well as it does to the individual estimates. So that suggests that we can use a z-test. So remember, for the z-test, we look at the difference of observed minus expected divided by the standard error. And in this case, we would simply look at the observed difference and the expected difference and divide by the standard error of the difference. So we know what the observed difference is. That's just the difference of the percentages. And we can also figure out what the expected difference is, because under the null hypothesis, these two are the same, so the difference is 0. And then the question is, what's the standard error? That's really the only thing that's new here. It turns out that if the two proportions are independent, that means the two samples were taken independently, then the standard error of the difference is we take the standard error of the first one, square it, take the standard error of the second one, square it, and take the square root of the sum. So let's plug this in. We get the difference of the percentages minus 0 on the top, and then we have the formula on the bottom. And now we simply use the formula for the standard error of a proportion, which is this thing there, and we have to square it. And now we have to simply estimate P1 by the percentage. We estimate P2 by the percentage, and what we get is 1.48. So now we can find a p-value by looking up a normal curve. We take 1.48, we look up the area to the right. Turns out that this is 7%, and the p-value is simply double of that, which is 14%. And of course, this is quite large, and so we cannot reject the null hypothesis. So we can use the formula for the standard error of a difference to also do a confidence interval. So this would simply be the observed difference of the percentages plus minus z times standard error. And then we can simply plug in the formula, and what we get is negative 1% to 7% in case z equals 2, that is, if we have a 95% confidence. Again, this assumes that the two samples are drawn independently. So it turns out that if we do hypothesis testing and assume that the two proportions are equal, then we can actually improve the estimate of our standard error somewhat. And that's done by what's called pooling. The idea is that we should simply combine our two samples to estimate this proportion P1, which is the same as P2. And the fact that these two proportions are the same allows us to combine the samples. So let's do that. We have 55% of 1,000, which is 550 voters in the first sample. In the same way, we get 870 in the second sample who approve. So in total, there are 1,420 approvals out of 2,500. And then our pooled estimate is simply the fraction of those who approve out of the total sample size of the combined samples, and that's 56.8%. And then we can compute the standard error of the difference using the formula we had before, but now what we do is we plug in this new number instead of the two different numbers. And what we get is 0.02022, which is almost the same as we got before. Now, if you were to compare two means instead of two proportions, then the whole thing works really just in the same way. So again, we get a formula for the standard error of the difference of two means, and that looks just like before. And remember, the standard error of an individual mean is the population standard deviation divided by the square root sample size. So in this case, n1 is the sample size of the first sample. And of course, we would estimate sigma 1 by S1, which is simply the sample standard deviation in the first sample. Now remember, if the sample size is not large and we have to estimate sigma, then we said we have to use a t-test instead of a z-test. And the same thing applies here. So if both sample sizes are not large, then we need to find a p-value using a t-distribution, and there's a complicated formula for that which you need to look up if you ever need it. If you look up the two-sample z-test in textbooks, then sometimes you see that there's some pooling going on if one can assume that the two standard deviations are the same. In that case, it's possible to estimate the common standard deviation using a pooled estimate whose formula is given here. However, it turns out that typically there's not much advantage of doing that. Also remember that this analysis rests on the assumption that the two standard deviations are the same, and there may be questions about that. And for these reasons, the pooled t-test is usually avoided. Again, remember that all of these two-sample tests we looked at require that the two samples are independent. It turns out you can also use a two-sample test in other special situations where the samples are actually dependent. For example, if one wants to compare the treatment effect when subjects are randomized into treatment and control groups. This is a special topic which you need to look up in case you ever come across it. Now let's look at these questions. Do husbands tend to be older than their wives? Well, we can collect some data, and here are the ages of 5 couples. What you see is, well, there's a husband of age 43, whose wife is 41, so there's a 2-year age difference. And then we have a couple where the husband is 71 and the wife is 70. Then we have 32 and 31. 68 and 66 and 27 and 26. So it looks like the husband is always a little bit older than his wife. So how would we analyze those data? Clearly we have two samples. There's the sample of the husband's ages, and then there's the sample of the wife's ages. But of course the problem is that in this case the two samples are not independent. The reason they are not independent is that while the husband's age is typically a bit larger than the wife's age, they tend to be closer together. For example, here the couple is both in their 70s, and then there's another couple in their 20s. So this similarity in age makes the two samples dependent. So this one major assumption of having two independent samples is not met in that case. But even if we could use the two-sample z-test, it would probably be not significant. And the reason is that the age differences are quite small, but the variation within each group is quite big. For example, husband's age are 43, 71, 32, so there's quite some fluctuation in there. And what the two-sample z-test does is it compares the differences to the fluctuations within each population. And in this case, the differences are small compared to the fluctuations within each population. It turns out there's a very simple solution for these type of data. Since we have pair data, we can simply analyze the differences obtained from each pair with a simple t-test. So again, let's start out with specifying our null hypothesis, which would be that the difference in population means is 0. Then the t-test would look at the average of the differences, subtract off the expected value, which is 0 under the null hypothesis, and divide by the standard error of the average. Now, the formula for the standard error of the average is the standard deviation in the population of the differences divided by square root sample size. And again, we would simply estimate sigma by the sample standard deviation of the differences, which is 0.55. Plugging this in, we find that our t-statistic is 5.69. Now we look up the t-table on some software, and what we have to do is we have to find the area to the right in the t-table from 5.69 on. And again, this curve is a student t-distribution with 4 degrees of freedom, which is 1 less than the sample size. And we would look that up and find the area there is 0.2%. So the p-value in this case is double that, which is 0.4%. And clearly this is strong evidence to reject the null. So it turns out that the paired t-test is very powerful in that situation. Again, remember that we do not need an assumption of independence between the two samples. Rather, what happens here is that the independence assumptions is in the sampling of the pairs. Now, what would happen if we didn't know the age difference, but only if the husband was older than his wife or not? In that case, we can still assess the evidence. We would have to write the null hypothesis a little bit different. We would say half the husbands in the population are older than their wives. And the reason why we write it down that way is because we are now only interested whether the husband is older or not, and we specify the proportion of husbands who are older, which is half. So that hints that we are looking 0-1 labels because we are counting how many husbands are older than their wives. And then we can just use a simple z-test. Remember, this is really the same thing that we looked at when we tested whether a coin is fair. So the z-statistic is simply the sum of the ones minus the expected values, and so we have n trials, and each has chance of a half of coming up 1, divided by the standard error of the sum. So in this case, a label 1 would mean that the husband is older than the wife, and a label 0 would be the other way around. So the z-statistic is 2.24, and now we can draw a normal curve, and we have to look up the area to the right of 2.24, and that area is 1.25%. And the p-value is double that. So it's still significant, but not quite as significant as the one before. The reason why it's not as significant is because we don't use the information that's contained in the age difference. We only use the information whether the husband is older or not. This test is very famous. It's called a sign test. The way to think about it is the coin tossing example we looked earlier. The coin tossing analogy makes it very easy to interpret the sign test, even for people who are not experts in statistics. And that's one of the main reasons why it's so popular.
Data science to me is more of, it's a tool in the toolbox, okay? And so, as a carpenter, you can build framing for houses, you can build, wooden fences, you can make wonderful custom cabinetry, you can make children's toys, but all of that comes out of sort of having that basic knowledge of how to use those woodworking tools. But there's obviously a lot of mastery that goes into those different disciplines. And so for us, it's more than just the knowledge of how to use these tools and how to explore data sets and make meaningful predictions or pull insights from them, but rather that has to be connected to medicine and biology and sort of this interpretive aspect of what we're doing. And so when we look for people that we bring into our company from the science perspective, not only do they have to have that meaningful understanding of computer science and sort of, how to use these tool sets, but also what are even the questions we want to ask of that data, or how are we going to construct these systems to sort of go after solving these very, complex biological problems. We're looking for that capability, in the minds of a single person.
Computer power has revolutionized statistical inference. In this module, we look at the two main concepts that are behind this revolution: the Monte Carlo method, and the bootstrap. We will discuss the main principles behind these methods and then see how to apply them in various important contexts, such as in regression and for constructing confidence intervals. Remember that very simple formula for the confidence interval for a population mean. We simply take the sample mean plus minus z times standard error. The reason why we used z was because the sample mean approximately follows the normal curve. Now what happens if we are interested in a different estimator, let's call it theta hat, for some parameter theta of the population, and the normal approximation is not valid for this estimator. In that case, such a simple formula is not applicable anymore and we have to do something else. Likewise, the simple formula for the standard error of the mean, which was based on the square root law, may not work anymore. So then what's the standard error in that case? It turns out that in such situations, simulations can be used to estimate those quantities. In fact, it may turn out that simulations sometimes result in better estimates than what we would have gotten if we would be able to use the formula for the normal approximation. Let's look at a simple example to see what the famous Monte Carlo method does. What's the average height of all people living in the United States? Well, this is impossible to determine exactly because we would have to measure the heights of all people in the United States. But we've already seen that we can actually estimate that average quite well. All we do is simply take a sample of size 100, and then we use the average height of that sample as an estimate of the average height of all the people. Remember, we talk about a parameter like theta when we talk about the population. So in this case, theta would be the average height of the population. We estimate that parameter theta with a statistic, which we call theta hat. And that statistic is based on a sample. In this case, our statistic would be simply the average of the sample. We already know that the sample mean tends to be close to the population mean, even for moderate sample sizes such as 100. And that's because of the law of large numbers. This is a simple example of the Monte Carlo method. Sometimes it's simply called simulation. What that method does is it approximates a fixed quantity theta by the average of independent random variables that have expected value equal to theta. Then, by the law of large numbers, the approximation error can be made as small as you wish by using a large enough sample size. It turns out that the Monte Carlo method can also be used for more complicated quantities. One quantity which is important in statistics is the standard error of a statistic. Remember that the standard error tells you roughly how far off the statistic will be from its expected value. There's a formal definition of the standard error which is given there. It's simply the square root of the variance when we think about theta hat as a random variable. So how would the Monte Carlo method work to estimate the standard error in this case? In the first step, we would get many, let's say 1,000 samples of 100 observations each. Remember, we take 100 observations each because the standard error of theta hat is the standard error when theta hat is based on 100 observations. Next, we compute theta hat for each of these 1,000 samples. And that gives us 1,000 copies of these estimates, which we call theta hat 1 up to theta hat 1,000. Finally, we simply compute the standard deviation of these 1,000 estimates. The formula you see there is simply the formula for the standard deviation. The average of these estimates is simply theta hat bar. Remember, the bar notation denotes averages. I didn't want to put two superscripts on there to make it not too confusing, so I wrote down the average of the theta hats. So now this is not an average of independent random variables, because the average of the theta hats is part of each of these terms. And so that makes the whole thing dependent. But the Monte Carlo method still works. It turns out that this quantity is roughly equal to the standard error. So while this example looks a bit more complicated than the previous one, what's really going on here is that it's simply an application of the law of large numbers. But the caveat is that this method will only work if we can draw many samples of size 100. In other words, simulation works if I can sample as much as I wish. The bootstrap pushes this a bit further. It makes it possible to use Monte Carlo sampling even in situations where I cannot draw as many samples as I wish. Let's look at a simple situation where I have an estimate theta hat, and I want to know what the standard error of theta hat is. To explain how the bootstrap works, let's first look at the so-called plug-in principle. In the example we had earlier, we were interested in the average height of all people in the US, and we estimated that with the average height theta hat of 100 randomly selected people. This simple step already illustrates the plug-in principle. We can't compute the population mean because there are over 300 million people and we cannot possibly measure all of their heights. So what we do is we plug in a sample of size 100 in place of the population, and we simply compute the mean of the sample instead of the mean of the whole population. So let's look at what we did here in terms of histograms. There was a population histogram, which is the histogram of the heights of all the people in the United States. The task was to compute the average of that histogram, and that's impossible to do. So what we did is we drew a sample of size 100. We looked at the histogram of the sample, and we used the average of the sample histogram in place of the average of the population histogram. The reason why this works is because the histogram of the sample tends to look very similar to the histogram of the population. That's really the key idea behind the bootstrap. And we will see how this idea can be used in all kinds of complicated situations. The bootstrap uses both this plug-in principle and Monte Carlo simulation to approximate quantities of interest, such as the standard error of a statistic. To explain how it works, remember how we used Monte Carlo simulation to estimate the standard error of a statistic. If I can draw a sample x1 to xn, then I can compute my estimator theta hat based on that sample. If I can sample as many times as I wish, then I can repeat this process many times, let's say 1,000 times, and I get 1,000 copies of my estimator. We saw earlier when we discussed Monte Carlo that the standard deviation of these 1,000 estimates is close to the standard error of my estimator, and that's simply because of the law of large numbers. But remember, the caveat in Monte Carlo was that we only have one sample, and we cannot sample as many times as we wish. The trick that the bootstrap uses is the plug-in principle. It simply simulates from the sample histogram instead of from the population histogram. In other words, the bootstrap pretends that the sample histogram is the population histogram and then simply uses Monte Carlo. So how does that work? Drawing a sample from the sample histogram means drawing with replacement from the n numbers x1 to xn. Let's call those numbers x1 star to xn star. That means x1 star is drawn at random from these n numbers x1 to xn, and likewise x2 star is drawn as random, and x3 star is drawn at random. Such a bootstrap sample x1 star to xn star has numbers that are among the sample x1 to xn. Some of the x's may come up several times, and others may not come up at all. Now what the bootstrap does is it draws capital B bootstrap samples and computes the estimator for each bootstrap sample. So we draw a bootstrap sample just as explained above, simply by drawing with replacement from the original data. We evaluate our estimator and we call this thing theta 1 hat star. Then we repeat the whole process capital B times, let's say 1,000 times, and we come up with 1,000 copies of these estimators. Then we use these 1,000 copies to approximate the quantity of interest, just as we did in the example of Monte Carlo simulation. For example, we would approximate the standard error of theta hat by the standard deviation of these 1,000 estimates. So in other words, the bootstrap uses two approximations. In the first approximation, it replaces the population histogram by the sample histogram. In the second approximation, it does Monte Carlo in order to approximate a quantity by the law of large numbers. Drawing a bootstrap sample by sampling with replacement from the data is called non-parametric bootstrap. Sometimes we know more about the data. For example, we may know that the data follow a normal distribution, but we don't know the mean or the standard deviation. In that case, we may want to use that information. Of course, the obvious thing to do there is to simply estimate the unknown mean and standard deviation, and then simply sample from the normal distribution with that mean and standard deviation. That's called parametric bootstrap. This type of sampling works if the data are independent, that is, x1 to xn are really generated independently. But oftentimes there's dependence in the data. For example, the data are observed over time. There are also bootstrap methods for dealing with that, but that's a somewhat specialized thing which we don't discuss here. Remember the simple formula for an approximate confidence interval. We take theta hat and then we go a multiple z times the standard error in each direction. So if we have a 1 minus alpha, for example, if alpha is 5%, we get a 95% confidence interval, then we would look z alpha half, so we would look at a normal curve, and alpha half is 2.5%. So we would look at z.025, and we would simply plug this into the formula and get an approximate 95% confidence interval. We just saw how to estimate the standard error in case there's no formula for it. But remember, the confidence interval is really based on the assumption that the sampling distribution of theta hat is roughly normal. That's the reason why we use the multiplier z from the normal curve. What happens if theta hat is not approximately normal? Well, it turns out we can use the bootstrap in a more ambitious way. In fact, we can estimate the whole sampling distribution of theta hat, not just the standard error. The idea is that the sampling distribution of theta hat should be close to that of the bootstrap copies. And the sampling distribution of the bootstrap copies I can get simply by generating many bootstrap copies and making a histogram of those. This histogram may be quite far from normal. For example, it might look skewed like this. But I can simply find a 95% confidence interval by looking up 95% in the middle and looking at the appropriate cutoff points at each end. This is called the bootstrap percentile interval. You simply look up the right percentiles on each end, so you have 1 minus alpha in the middle. An alternative way to do that is not to bootstrap the distribution of theta hat, but to bootstrap the distribution of theta hat minus theta. Why would one do that? The hope is that this is less sensitive to the particular value of theta, and therefore it may produce a more accurate confidence interval. The resulting confidence interval is called bootstrap pivotal interval, and the formula is given there. Now let's look at bootstrapping in a more complicated situation. Let's look at the case where we have pairs of data and we look at a regression model. Remember, our regression model says that the y observation is a linear function of the axis plus a measurement error e. We already saw how we can use these squares to estimate the unknown parameters a and b, and that gives us least squares estimates a hat and b hat. Now we would like to have some standard errors for these estimates. How would we use the bootstrap to do that? The key point here is that we don't resample the whole pairs of observations, but rather we resample the error terms. Now, of course, we don't know the error terms, but what we can do is we can use the residuals in place of the error terms. Remember, once we fit a regression line and we have observations of the line, then the residuals are simply the vertical distances to the line. And if the regression line is a good estimator, then the residuals should behave similarly to the unknown error terms. While the error terms E are unknown, we do know the residuals because we fit the regression line. So we can draw a bootstrap sample from those residuals, and we get n bootstrapped residuals E star 1 to E star n. In the next step, we pretend that the estimated regression line is the true line, and we add on the bootstrapped residuals. That generates a new set of observations y star. So the x's stay the same, but the y stars are now different because they are generated from the x's and the estimated regression line with the bootstrap residual added on. This gives us a bootstrap sample x1, y1 star up to xn, yn star. And from that sample, we can estimate the parameters a hat and b hat in the usual way by least squares. And now we follow the usual bootstrap algorithm. We repeat this whole process 1,000 times, and then we estimate the standard error of a hat by the standard deviation of these 1,000 estimates a hat star, and likewise for b hat. Categorical data come up when observations are grouped into categories and organized into tables. We will look at 3 important statistical analyses for categorical data: tests for goodness of fit, homogeneity, and independence. This module is about categorical data. To see what categorical data are, let's look at this big tragedy from 1912 when the Titanic sank and more than 1,500 of the 2,229 people on board died. The question we can have is whether the chance of survival depended on the ticket class. It turns out very detailed data are available about the Titanic disaster. Here is a table that shows the number of survivors and people who died for each ticket class, as well as for the crew. This is a typical example for categorical data. The data are given as counts for a fixed number of categories. Typically, such data are obtained by grouping. In this case, the data are tabulated in what's called a 2x4 table. That's because there are 2 rows and 4 columns. Such a table is also called a contingency table because it shows the survival counts for each category of ticket class. That means contingent on the ticket class. We will look at 3 problems that involve categorical data. They all use the chi-square test. These problems are testing goodness of fit, testing homogeneity, and testing independence. M&M candy comes in different colors. The company that produces M&Ms actually put the percentages of the various colors on the website. But in 2008, they stopped publishing those data. Here are the last data that were published in 2008. It shows the percentages for each of the 6 colors: blue, orange, green, yellow, red, and brown. So a question is whether that's still the distribution of colors today. A group of students opened a bag of milk chocolate M&Ms and counted the colors. And here's the table of the counts which they got. So we would like to answer the question whether these counts are consistent with the last published percentages, or whether there is sufficient evidence to claim that the color distribution is now different. This type of problem is called a goodness of fit test. The question here is whether the observed data fit the published distribution. As always when testing, we have to think what the null hypothesis is. Remember, the null hypothesis means that nothing special is going on. And in that case, that would mean that the color distribution is still the same that it was in 2008. The alternative hypothesis would be that the color distribution is different. The idea of a goodness of fit test is to compare the observed counts to the numbers one would expect if the null hypothesis were true. In order to do that, we need to figure out what the expected number under the null hypothesis would be. Now that's a very simple calculation. We have 410 M&Ms in our bag, so under the null hypothesis, we expect 24%, which is the percentage given in the table, times these 410 counts, which is 98.4 blue M&Ms. So now we do this for all the other 5 colors, and then we have a table for expected counts. And remember, we also had a table for the observed counts. So next we have to compare these 2 rows of observed and expected counts and see whether those numbers are compatible with each other. The way we do that is we look at the difference between observed and expected counts, then we square it to make it non-negative, and then we standardize it. And it turns out that in order to standardize, here we have to divide by the expected counts. We do that for each category, and we sum up these terms over all categories. So for example, for the blue M&Ms, we observed 85, we expected 98.4, and so we take the difference of these 2, square it, and divide by expected. We do this for all 6 colors, and the statistic, which is called a chi-square statistic, is then 8.57. If the value of that chi-square statistic is large, that means there's a big discrepancy between observed and expected counts, and that's evidence against the null hypothesis. On the other hand, if the chi-square statistic is small, that means that the observed and expected counts are close to each other. Next, we compute a p-value. That means we have to assess how large that 8.57 is when compared to an appropriate null distribution. In this case, it turns out the null distribution is called the chi-square distribution, which comes with the degrees of freedom, and the degrees of freedom is the number of categories minus 1. So in this case, we have 6 colors, so the degrees of freedom is 5. On the right-hand side, you see the curve for the chi-square distribution with 5 degrees of freedom, and our value of the chi-square statistic is at 8.57. So the p-value is the area to the right of that, which turns out to be 12.7%. So the conclusion here is that there is not sufficient evidence to reject the null hypothesis. The assumption of the chi-square test is that the observed data are counts that were obtained by drawing independently from a population. It's plausible that filling a bag of M&Ms roughly corresponds to this process. As an interesting fact, the blue M&Ms were not introduced until 1995. In the beginning, some people suspected that there were fewer blue M&Ms in the bag than advertised. Of course, we can also test that. This is a case which we looked at before, because if we are just interested in one category, then we can simply use a z-test. So the chi-square test is in a sense a generalization of the z-test if you want to examine several categories. Here's a different question about colors in M&Ms. Is the color distribution the same for milk chocolate M&Ms, peanut M&Ms, and caramel M&Ms? So in this case, we would have to compare several populations. That is called a test of homogeneity. The null distribution is that the color distribution is the same for all of the populations, which in this case are milk, peanut, and caramel. The chi-square test of homogeneity assumes that the samples are drawn independently for each population and also independently across the populations. To see how the mechanics of the test work, let's look again at the survival data for the Titanic. The first thing to note is that we are not sampling from a population. The data we have are not a random sample of the people on board, rather the data represent the whole population. So this is not the usual setup where we sample from a population. But it may still meet the assumption that we draw independently. The way to think about this is that the chance process resulting in survival or death is the result of a sequence of random events that occurs when people try to find their way out of the ship, get into a lifeboat, or have to jump into the water, and whether they are being rescued out of the water in time. So we can think about the 325 observations on first-class passengers as 325 independent draws from a probability histogram that gives a certain chance for survival. Likewise, the 285 observations about second-class passengers are drawn from a probability histogram for second-class passengers, which may be different. Now, the null hypothesis says that the probability of survival is the same for all four probability histograms. And that's the null hypothesis we are going to test. The chi-square test in this situation is quite similar to the one before. That means we compare the observed counts to expected counts. We already have a table of observed counts, so next we have to find the table of expected counts. The way this is done is that realizing that under the null hypothesis, the probability of survival is the same for all four populations. That means we can estimate the probability by simply pooling all the data. In total, there were 713 survivors among the 2,229 people on board. So we estimate the probability of survival as 713 over 2,229, which is 32%. Then the expected number of surviving first-class passengers is that 32% times the number of first-class passengers, and that comes out to be 104. We repeat this calculation for the other 7 categories, and that gives us our table of expected values. Then we compute the chi-square statistic just as before. That is, we look at the difference between observed and expected, square it, divided by expected, and sum over all 8 cells. In that case, the chi-square statistic gives us 192.2. Again, we have to compare this number to a chi-square distribution, but the degrees of freedom in this case it's different. The degrees of freedom is given by the number of columns minus 1 times the number of rows minus 1. So we had 4 ticket classes, so we had 4 columns, so 4 minus 1 is 3. And then we had 2 rows, 2 minus 1 is 1, so the degrees of freedom is the product of 3 and 1, which is 3. So then we have to compare the chi-square value of 192.2 against a chi-square distribution with 3 degrees of freedom. If you look at the picture, you see that this 192 is all the way out there, and there's essentially no area to the right, so the p-value is 0%, and that is very strong evidence against the null hypothesis. So the conclusion would be that the chances of survival depended on the ticket class. Finally, the third application of the chi-square test is testing independence. As an example, we may ask whether gender, being male or female, is related to voting preference. That means voting liberal or conservative. In this case, we have 2 categorical variables. One is gender and the other is voting preference. The null hypothesis is that the 2 variables are independent. The alternative hypothesis is that there's some kind of association. Again, the chi-square test can be used to test this null hypothesis. We sample data from the population by sampling people at random. We record the outcomes for the 2 categorical variables, and that gives us counts in a 2x2 table. It turns out that the chi-square statistic and p-value are computed exactly as in the case of testing homogeneity. That means we also use the same way of computing the degrees of freedom. Since the chi-square test works the same way both for testing independence and testing homogeneity, it's easy to mix those up. Here's a table that compares what's different between these two cases. The first difference is in the sampling. The chi-square test of homogeneity measures a single categorical variable on several samples that were obtained from several populations. In contrast, for the chi-square test of independence, we have only one sample, but we measure two categorical variables on this sample. Also, the research questions are different. The chi-square test of homogeneity tests whether the different groups are homogeneous, which means that they have the same distribution of the categorical variable. In contrast, the chi-square test of independence checks whether the two categorical variables are independent. Some people have suggested that when a student is grading other students' homework, there might actually be a substantial learning effect. Recently, an experiment was done to figure that out. Students were randomized into 3 groups, with each group spending the same amount of time per week. One group did homework only, the second group did homework and peer assessment, and the third group simply studied without doing any homework. The final exam scores of that class were summarized by 3 box plots. You can see from the box plots that the 3 medians differ somewhat, but the question is whether that is sufficient evidence to conclude that the 3 treatments result in different outcomes. Of course, in this case, the null hypothesis of nothing extraordinary is going on simply means that all groups have the same treatment mean. Now, if we had only 2 groups, then we already know how to attack that problem. We would simply use a 2-sample t-test. In that case, the t-statistic looks at the difference in the 2 sample means and compares it to the standard error of that difference. What we do in this module is we generalize this idea to the situation where we have several groups. This methodology is called ANOVA. To explain the idea behind ANOVA, let's consider 2 hypothetical outcomes to our experiment. In the left display, we have a situation where the differences between the sample means are large relative to the variability within the groups. That means the difference between the first and the second mean is this, between the second and the third is this, and between the first and the third it's this one. And these differences are large compared to the variability within each group. For example, the variability in the third group is roughly this one, the variability in the second group is that one, and the variability in the first group is this one. So this suggests that there's evidence that the means in the 3 groups are different. In contrast, in the situation on the right display, we see that the differences in the means is quite small compared to the variability within each group. This suggests that the differences in the mean may simply be due to sampling variability. So the idea here is to compare the sample variance of the means to the sample variance within the groups. Remember, the sample variance is simply the square of the sample standard deviation. This is why this whole methodology is called analysis of variance. However, things are not so easy that we can simply look at the box plots. The reason is that because of the square root law, the chance variability in the sample mean is smaller than the chance variability of the data. So we have to do some kind of computation to assess the situation. If we have k groups, we write down the data as follows. The observations of the first group go into the first column, and each observation has 2 indices. The first index simply counts the observations, and that's from 1 up to some number n1. And the second index simply means we're in group 1. We do the same thing for group 2, so there are n2 observations in the second group, all the way up to group k, where there are nk observations. So in particular, this means there doesn't have to be the same number of observations in each group. In total, there are capital N observations, which is simply the sum of the little n's. Finally, y bar sub j is simply the mean of the jth group. And y bar bar is the overall mean, which is also called the grand mean. The analysis of variance computes 2 important quantities: The first one is called the treatment sum of squares. There, we look simply at the difference of the jth group mean to the overall mean, we square the difference, and then we sum up over all rows and columns. This term has k-1 degrees of freedom. If we divide the term by its degrees of freedom, we get what's called the treatment mean square, MST. The treatment mean square is essentially the sample variance of the treatment means. So it measures the variability of the treatment means y bar j. The other quantity we are interested in is the error sum of squares. For that, we look at the square difference of each observation and its corresponding group mean. And then again we sum over all rows and columns. This term has n-k degrees of freedom. Again, dividing by the degrees of freedom gives what's called the error mean square, and that measures the variability within the groups. So these two terms, the treatment mean square and the error mean square, make formal the idea we had on the previous slide, where we look at the variability between the treatment means and the variability within the groups. Since we are interested in how these two measures of variability compare, we simply look at the ratio. And that ratio is called the F statistic. Under the null hypothesis, where there is no difference in treatment means, this ratio should be about 1. Of course, it will be not exactly 1 due to sampling variability. In fact, it follows what's called an F distribution with k-1 and n-k degrees of freedom. So the F distribution is a little bit like the student's T distribution in that it comes with degrees of freedom, but in this case there are actually 2 degrees of freedom, one for the numerator, which is k-1, and one for the denominator, which is n-k. Remember, our idea is to assess whether the variability between the treatment means is large compared to the variability within the groups. So we would reject our null hypothesis if this F statistic is large. And that means that if F is in the right 5% tail, that is when the p-value is smaller than 5%. Typically, the result of an analysis of variance are summarized in an ANOVA table. Remember, we looked at 2 sources of variation, the treatment and the error, which is the variability within the groups. We saw the treatment has k-1 degrees of freedom, and the corresponding treatment sum of squares are denoted by SST. The mean square is simply the treatment sum of squares divided by the degrees of freedom. The same thing applies to the second line, where we look at the error sum of squares and the mean square error. And finally, we saw that the F statistic is simply the ratio of these 2 mean squares. And then the analysis will produce a p-value which goes in this last cell here. There's also a third line in the ANOVA table which simply sums up the degrees of freedom and the sum of squares, and we will talk about that later. In the previous example about peer assessment, when we do the ANOVA for the data in the right-hand display, we get the following ANOVA table. The p-value comes out as 9.7%. Since that is not smaller than 5%, there is not sufficient evidence to reject the null hypothesis. Remember, that was also our impression when we looked at the box plots. The idea behind the ANOVA table is that each observation is generated as the sum of a treatment mean mu j and an error term epsilon. You can think of the error term as a measurement error, and the assumption for ANOVA is that these error terms at least roughly follow the normal curve, and they are independent with mean 0 and a common variance sigma square. Remember, our null hypothesis is that all those treatment means are the same. Instead of looking at these treatment means mu j, it's common to look at deviations from an overall mean mu. That deviation is called tau j. It's simply the difference of the j's treatment mean from the overall mean mu. So if we rewrite that model, we get that an observation yij is a sum of the overall treatment mean mu, the treatment effect of the jth group, and the error term epsilon. Since we are now looking at deviations from the overall treatment mean mu, the null hypothesis becomes that all these deviations are 0. Of course, we would estimate the overall mean mu by the grand mean y bar bar. Then the estimate of the treatment effect tau j simply becomes yj bar minus y bar bar. All we did there was plugging in the estimates for mu j and mu. Finally, the estimate of our error term epsilon is simply the residual. The residual is defined just the same way as in regression. So now when we look at our model where y is the sum of an overall mean mu, a treatment effect tau j, and an error term, we can plug in our estimates and we get this equation. Y is the sum of three terms. Now, of course, this is kind of obvious because you see that y bar bar cancels out here, and the jth treatment mean also cancels out. So this identity simply says that yij equals yij. But it's useful to write it that way because it tells us how we think that yij comes about from the various sources of variation. It turns out that this type of decomposition is also true after squaring terms. That is, after we move y bar bar to the left side by subtracting it off, and then if we square and take sums, we get this identity here. We already know what the last term there is. That's simply the error sum of squares. Likewise, the second to last term is the treatment sum of squares. We haven't discussed the first term. It's called total sum of squares. If you look at this, you see what we are doing here. We look at all the observations, look at the squared differences from the overall mean, and sum up. So this is like a formula for computing a sample variance. What this means is that the total variation can be split into two sources: the treatment sum of squares and the error sum of squares. This is the decomposition that's behind the ANOVA table. Here are some more important points on ANOVA. The F-test that we looked at assumes that all the groups have the same variance sigma square. This needs to be checked. One way to roughly check it is simply look at the side-by-side box plots. But there are also formal tests that can be used for that. Another assumption that we used was that the data are independent within and across groups. If the data we get are the results of a randomized controlled experiment, then this randomization condition would be met. On the other hand, if the data were obtained from an observational study, then we have to be careful with the analysis. Not only may the assumptions not be met, but we have to be careful with the conclusion, because remember, if we have an observational study, we cannot conclude that there's causation going on, because there could be confounders. Finally, suppose we do the ANOVA and the F-test rejects. So the conclusion is that the group means are not all equal. The next question then is, how are they different? One way to look more closely at those differences would be to use two sample t-tests comparing all possible pairs of means. In this case, one would use the pooled standard deviation for the t-test. This is simply the within-group variation, so it's the square root of the error mean square. But since we would look at many of such comparisons, we have to be a little bit careful with our tests and have to make an adjustment. We will talk about this in the next module.
Yeah, I think for new people that come into the field, you'll quickly realize that there are massive amounts of tools that you can use, whether that's choices in database technologies, language to process those database systems with, different machine learning algorithms, and so that can be very overwhelming. Just to sort of examine all of the possibilities of what you could use from a language perspective, tools perspective, etc. My advice would be start small, gain expertise in a particular tool or in that area, and then expand. I think that there's a reason why so many different languages have been built over the years and so many different database technologies. They all solve very different problems. And as you become more and more of an expert in understanding these tools, when you go to solve a problem, you can pull out the right tools from the toolbox and piece them together to get the best solution. And so that breadth of understanding, again, it can become very overwhelming at times, but I wouldn't let that scare you. I would actually encourage you to try to explore as many of those things as you can. Data for me in data science is a way to sort of understand our world And it can be applied to so many different things. And so if you have passion as an educator, or passion as someone who's interested in sports or cooking, or in my case medicine, there is work to do in data science in all those fields and many more. What's very important in choosing a career is to have some passion behind it. If you have a passion for women's basketball and you have a passion for data science, in that field you will be a hero, right? Because you're going to be able to come in and, whether that's doing the meta tagging or looking at, statistical information of other sports teams in the past, you can bring that analysis to bear and help that sports team perform better, train better, be better prepared for that next game in ways that other people can't, right? I think part of what's hard for us to sort of understand as humans is there is some very serious limits to what our brain can do. It can be so easily fooled, right? Like we believe we can win the lottery. We believe, we're going to die in an airplane when, the most likely thing to do, of course, is to die in an automobile accident. No one gets scared jumping into their car. And so that capability to go beyond what humans can think about on their own, to process data and bring new insights to whether it's a basketball game or any other discipline, is a very powerful thing, and that can be applied to nearly any endeavor that humans engage in.
The era of big data has led to a crisis of replicability and reproducibility, which has hit the mainstream news and which has even led some to question the scientific method. We will discuss some of the important causes of these problems and how to guard against them when doing statistical analysis. So what is data snooping? Let's look at a famous Swedish study from 1992, which examined whether living near power line causes adverse health effects. That study reported a statistically highly significant increase in childhood leukemia. But then curiously, when people followed up on that study, it turned out they couldn't really confirm that result. So why then did that study result in such a statistically significant outcome? To understand what's going on, we have to keep in mind that the study looked at 800 different health effects. That means the way to think about it is that the study did 800 different statistical tests. Remember that the p-value summarizes the evidence for an effect, and the interpretation is that the smaller the p-value, the stronger the evidence. In particular, if the p-value is smaller than 1%, then one says that the test is highly significant. But keep in mind what that means. It means that if there's no effect, then there's still a 1% chance to get such a highly significant outcome. But that means that if we do 800 tests, then even if there's nothing going on at all, we would expect to see about 800 times 1%, which is roughly 8, highly significant outcomes just by chance. This is what happened in that Swedish study. They did so many tests that they found highly significant outcomes even if there's nothing going on there. This effect has a name. It's called the multiple testing fallacy, or the look elsewhere effect. With the large amounts of data that are available nowadays, it's very easy to fall into this trap. The reason is that there are just so many potential relationships one can look into that one sooner or later will run across a test which is significant just by chance. This behavior is called data snooping. One way people find out that data snooping was done is if they cannot replicate the study. Replicating means to get the same conclusion with slightly different samples, procedures, and data analysis methods. Related to that is the problem of reproducibility. That means to get the same results when you simply use the same data and same methods that were claimed in the analysis. In past years, there have been some high-profile publications that discuss the lack of replicability and reproducibility. Two interesting papers are How Science Goes Wrong, which is an article in The Economist, and the research paper Why Most Published Research Findings Are False by John Ioannidis. So what can be done about this problem? We will look at three methods that account for multiple testing. The first one is called Bonferroni correction. It simply means that if you do m tests, you multiply the p-values by m. What that correction does is it makes sure that the probability of a type 1 error is still at most 5%. That means the probability of any of the m tests rejecting an error is smaller than 5%. On the other hand, the price you have to pay is that the p-values get bigger. After all, you multiply them by m. Note that this is a very restrictive condition. If you do a large number of tests, let's say m is 1,000, you guard against even having one false positive. A consequence of this is that it may be difficult to claim a significant finding, even if a noticeable effect is present. For example, if you do 1,000 tests and the p-value is, let's say, 0.1%, which would look quite significant, you have to multiply it by 1,000, and then it doesn't look significant anymore at all. So the Bonferroni correction is probably working well if you don't have a large number of tests to look at. There's an alternative way that's much more promising if the number of tests is large. And that has to do with the false discovery proportion, which is abbreviated FDP. That is the proportion of false discoveries over the total number of discoveries, where discovery simply means that a test rejects. That thing is best explained with an example. Suppose we test 1,000 hypotheses. So that picture shows 1,000 squares. Each one corresponds to one hypothesis. Now let's assume 900 of these hypotheses are null. That means there's nothing going on. And 100 of them are alternative hypotheses, so there is an effect there. In that picture, the alternative hypotheses would be the blue square on the top. So ideally what we would like to do is we would like to do a test for each of these 1,000 hypotheses, and we would like to find that the tests reject for the blue subsquares, but not for the green ones. So if we do that, we might get an outcome like this. The red squares are tests that reject, so those are resulting in discoveries. And the gray squares are tests that don't reject, so those are the non-discoveries. Now remember, a test can make two kinds of errors. It can reject a null hypothesis even though it's true. Those type 1 errors would be the red squares among the null hypotheses. For example, these. The second type of error a test can make is it can fail to reject a null even if the alternative is true. Those would be the gray squares among the right upper corner. So what you see in this picture, that among the alternative hypotheses in the right upper corner, the test does quite well. There's a few errors, but overall it finds all the alternatives. On the other hand, among the null hypothesis, there's quite a number of red squares, so the test makes quite a number of errors. But keep in mind that if we use a test that has a probability of a type 1 error of 5%, which is our usual threshold, then we would expect about 5% of the null hypothesis to be rejected in error. Since we have 900 null hypotheses and 5% should be rejected in error, we would expect to see about 45 false discoveries. And that's roughly what's going on in this picture. So that's not at all unusual. So if we tally up the results of this procedure, then we see among the area where the alternative is true on the right upper corner, we made 82 discoveries and we missed 20. And then among the null hypothesis, we made 41 discoveries, which are false discoveries. So the false discovery proportion is the fraction of the number of false discoveries, which is 41, divided by the total number of discoveries. And there we have 82 discoveries and 41 false discoveries. So the false discovery proportion is 41 over 121, which is 34%. And the procedure we discuss next tries to control this proportion. For example, it tries to keep it at 5%. So that means we may well allow some of the red squares, but we want to make sure that those false discoveries are a small fraction of the total number of discoveries. Here is how the procedure works. It's called a false discovery rate procedure, and it controls the expected proportion of discoveries that are false, just as we explained on the previous slide. That procedure was published in 1995 by Benjamini and Hochberg, so it carries their name. It consists of 3 steps. First, what you do is you sort the p-values. So you look at the smallest, which is p with a subscript of 1 in brackets, up to pm, which is the largest p-value. So this is simply a sorting of the p-values according to their size. Next, you look at the largest number k, such that the k smallest p-value is not more than k over m times alpha. And of course, you would simply write a small computer code to do that for you. And that's pretty much all, because in the third step, you declare discoveries for all tests I from 1 to k. That is, for the k most significant tests, you declare them to be true discoveries. It turns out that this very simple procedure controls the expected proportion of false discoveries at a rate of alpha. The third approach we are looking at is called the validation set approach. The idea is you split your data set into 2 parts. One is a model building set and the other is a validation set. Now you use the first part, the model building set, to find something interesting. So you may well use data snooping on that one. After you come up with a hypothesis, you test this hypothesis on the validation set. This is not anymore multiple testing because the test you did on the validation set is only one test, and the validation set is completely different from the model building set. However, that approach requires strict discipline. You have to be sure that you never peak at the validation set until right away at the end when you're ready to evaluate your test. We have reached the end of the course. We have discussed the key ideas for learning from data and assessing uncertainty. We looked at the important concepts that are behind almost every statistical inference, such as the square root law and the basic rules of probability. We also saw how modern computer-intensive procedures, such as the bootstrap, can be a big help for inference. We discussed the main statistical procedures that come up in analyzing data, such as regression, testing, and the analysis of categorical data. We also discussed how to effectively communicate information by visualizing data. Even advanced methods in machine learning use these basic ideas in one way or another, and chances are that when you look under the hood of new methodology that you encounter in the future, you will recognize a number of ideas that we discussed in this course. You now have the background to take the machine learning course or an advanced statistics course. I wish you the best with your future learning.